This is a very important section on training for per carrier H matrix estimation. In MIMO systems, it's very important to be able to provide training preambles from the transmitter to the receiver in order for the receiver to be able to estimate the channel based on the training symbols that are sent. This section is based on the Draft 802.11n, and its purpose is to provide a description of a system that can be used in order to train for the H matrix on a per carrier basis, and also so that you can understand how training is achieved in a MIMO system. Obviously, for different MIMO environments, for example in mobile WiMAX or 4G, other training mechanisms may be used, but in this case, by presenting the material here based on 802.11n draft, you can get a good understanding of how to perform training for a MIMO system. To begin, we show the packet for a high throughput MIMO packet in a 802.11n draft system. In this case, the packet consists of the PLCP preamble, and we're talking about a legacy preamble compatible with 11A systems. The preamble is 16 microseconds and includes the long training field that is typically used for 802.11a in order to estimate the channel, in order to then equalize the channel after the forward FFT. Following the preamble, we have the signal field, and this is a legacy signal field, which is 4 microseconds and uses BPSK modulation. Following the legacy single field, we have the high throughput single field. And following the high throughput single field, we have the high throughput short training field, which is used for AGC refinement, as we discuss in a separate section. Important for us is the fact that the short training field, the high throughput short training field, is followed by training symbols in order to estimate the channel H matrix, and the number of training symbols is related to the number of spatial streams. And here we show N training symbols. Following the N training symbols, we have the data, and again the data is modulated using a particular MIMO system that can be set up either for spatial multiplexing or diversity mode. The rate of the high throughput data is determined by the high throughput signal field, which we discuss in a separate section. The key point here is that prior to being able to demodulate the data, we have to obtain an estimate of the H channel in order for the MIMO equalizer to operate on the data after the FFT, and to be able to separate these spatial streams in the case of spatial multiplexing. Here we show the timing. We have on top here the legacy packet, where we have 8 microseconds for the short training field. L stands for legacy. We have 8 microseconds for the long training field. Recall that that was 2 symbols that are duplicates of each other, and we had a 32 sample cyclic prefix. We have the legacy single field, which is 4 microseconds, and then we have the legacy data. Now in the case of 802.11n, the draft, we have the legacy preamble, again an 8 microseconds short training field and a 8 microseconds long training field, the legacy signal, and that's followed by 8 microseconds for the high throughput signal, 4 microseconds for the high throughput short training field for AGC refinement, and then followed by the long training fields, the high throughput long training fields, which we are going to discuss, which are used to then estimate the channel H matrix on a per carrier basis, and that is used by the MIMO equalizer in order to separate these data streams. In order to separate the spatially multiplexed data streams, for example. Each HT long training field is 4 microseconds long. This is a very important diagram which illustrates the concepts behind training for the H matrix. Consider the H matrix for a 2x3 MIMO system. The idea is to estimate H11 and H12, in this case, for antenna number 1. We can also, once we've outlined how we can train for antenna number 1, we can train for antenna number 2 and antenna number 3. So let's focus on one receive antenna for now. The technique is based on the following. First of all, we have two symbols shown over here at two different time slots, time slot number 1 and time slot number 2. In this diagram, n equals 1 is the first symbol that is sent, and n equals 2 is the symbol that is sent following n equals 1. ITX is the number of the transmit antenna. We have two transmit antennas in this case, transmit antenna number 1, transmit antenna number 2, and the index is ITX. We'll show that later when we present the actual formula for the training symbols in the time domain for 802.11n draft. So we have one time slot n equals 1 and followed by another time slot n equals 2. The symbols shown here are weighted as follows. There's a matrix P which has entries. It's a 2x2 matrix in this case. It has 4 entries and we're showing them 1, 1, 1, minus 1. These are the weightings we're going to apply to these symbols. Now, even though we're showing OFDM symbols here, once we remove the guard interval and perform the forward FFT at the receiver, you can basically consider that we are estimating the H matrix on a per carrier basis. So if we have 56 carriers, for example for 20 megahertz bandwidth, if we have 56 carriers, then we are going to estimate 56 H matrices, one for each carrier. On a per carrier basis, the channel for an OFDM system can be considered to be flat fading. In this case, on a per carrier basis, each carrier, for example the carrier on the transmit chain number 1, goes through a multi-path fading channel and is received by the receiver. Assuming flat fading, it is multiplied by a complex number H1, and the carrier from antenna number 2 goes through a multi-path flat fading multiplied by a complex number H2. They are combined at the receiver, so at the receiver you have the symbols, the carriers multiplied by H1 or multiplied by H2. Now the carriers themselves for the training field have magnitude equal to 1. For a 20 megahertz system we have 56 carriers. So at the receiver we basically have, based on the weighting shown over here, at the receiver we have at time slot number 1 corresponding to here, we transmit the orange color here through the first transmit chain, and we transmit the color here for transmit number 2, and they are received at the receiver. So for time slot n equals 1, we receive R1 equals to H1 plus H2. Because of the weighting of P, we get H1 times, we get 1 times H1 plus 1 times H2. That's what we receive for R1. And the next time slot, shown in the blue in the case of the first transmit antenna, then if we collect these two received signals, R1 and R2, at the two different time slots, we can organize them into a vector. So we have a vector R1 and R2. Then R1 and R2 is equal to the matrix P, which is 1, 1, minus 1, 1, times the vector H1 and H2, which are the unknown complex channel frequency responses at the carrier, plus a vector corresponding to the noise in the receive chain. And here we're dealing with one antenna at a time, and we're estimating H1 and H2, which is the first row of the H matrix. For the remaining antennas in a 2x3 system, we would perform the same operation for estimating H21 and H22, and also for the third antenna, H31 and H32. If we pre-multiply the received vector R1 and R2 by the matrix shown here, which is the inverse of the P matrix, so we pre-multiply this vector by the matrix here, 1, minus 1, and 1, 1, and we have a 1/2 scaling factor. If we take this matrix and pre-multiply R1 and R2 by that matrix, then the multiplication of this matrix and this matrix with a scaling factor of 1, 2 produces the identity matrix. So you can see that, for example, for the first element we get 1 times 1 plus 1 times 1, and we get 1 times minus 1 plus 1 times 1, which is 0 for the off-diagonal element. So we get the identity matrix, which recovers H1 and H2, and we have this matrix here times n, the noise. And again, the noise vector is a 2 by 1 vector corresponding to the noise for R1 and R2 at the two different time slots. So clearly we have obtained estimates of the channel frequency response at that carrier, H1 and also H2. For example, if we assume that the noise is 0, this term drops out, and we get that H1 estimate is equal to H1 and H2 estimate is equal to H2. Of course, we do have noise, so there is noise in the estimates of the H matrix. So to summarize this part here, it's very important that in order to provide a mechanism for obtaining an estimate of the channel on a per receive antenna basis, based on the fact that we have two transmit streams, we basically have two symbols which are organized in two time slots, and they are sent using the matrix P in order to weight them. And as they're received, we receive a receive vector R1 and R2 delayed again in two time slots, n equals 1 and n equals 2, R1 corresponding to n equals 1, R2 corresponding to n equals to 2. If we organize them in terms of, and write them down in terms of the vector operations here, then once we receive R1 and R2, we pre-multiply them times this matrix here, which is the inverse of the P matrix, and we recover the estimate of the channels. Of course, these are noisy estimates. Now, very importantly, we have to point out that the matrix, the inverse of the P matrix, is a unitary matrix and does not enhance the noise. So that's one of the advantages of using the orthogonal method in order to train for the H matrix entries, is the fact that the orthogonal matrix that is used is actually unitary, and in this case it's real, so it's actually an orthogonal matrix. Then the noise is not enhanced. So this is a big benefit of this technique. So during the training, where we're sending the high throughput long training fields, each antenna would perform this operation and obtain its estimates of the channel, as you can see, from the transmit antenna to the receive antenna. And this is done for all 56 carriers, for example, for a 20 megahertz system. Once the H matrix is estimated, then it is used by the equalizer in order to compute the, for example, in the case of an MMSE equalizer, to compute the matrix W, which is then stored and applied to the incoming data portion of the packet in order to separate the spatial streams and achieve equalization. Since we have 56 carriers for which we need to obtain estimates of the H matrix for each carrier, then of course the high throughput long training field has at least 56 entries shown over here with a null at DC. And also in this table we show that the number of long training fields, the HT long training fields required to probe the channels, is related to the number of spatial streams. So if you have one spatial stream, we only need one long training field for the data. And if we have two spatial streams, we need two. If we have three spatial streams, we need 4 training fields. And if we have 4 spatial streams, we still need 4 training fields. Each training field is 4 microseconds long. Here we have a complicated expression for the time domain representation of the high throughput long training fields. We'll go over this very quickly. So basically R of t is the time domain representation of the long training field, and the index n is important because, as you recall, n was equal to 1 over 2, which is a symbol number. In the case of a 2 by 2 system, then n would range from 1 and 2 in case of two transmit trains. In the case of two transmit chains, ITX is the index for the transmit chain, so ITX in this case will range from 1 to 2. So Rn comma ITX, where ITX is either 1 for the first transmit chain and ITX is equal to 2 for the second transmit chain, and n is equal to 1 for the first symbol and n equals 2 for the second symbol. W of t is a weighting function. We'll ignore that. These are all constants because they're given the number of spatial streams and the number of tones, etc. These are constants. Let's ignore that. We have one expression here plus another expression here, and let me simplify things by first of all dealing with a 20 megahertz channel. If we look at this symbol over here, gamma, for a 20 megahertz channel, gamma is equal to 1, and if we make this 1, we can actually combine these two equations into one summation from k equals minus nsr to k equals plus nsr. However, we separate them because in the case of a 40 megahertz channel, then gamma would be equal to j. NSR in our case is equal to 28, which is equal to half the number of data carriers cut, which is equal to half the number of carriers in the bandwidth. So for 20 megahertz, that's equal to 28 since we got cut, since we have 56 carriers. This includes data plus pilots. And of course we have a null at DC. So we're basically summing over all the carriers, the expression here. And for each carrier, we're also summing over the number of spatial streams. So we have another sum here, which we have ISTS equals from 1 to NSTS, where NSTS, shown over here, is the number of spatial streams. So if we have two spatial streams, then we have a sum from 1 to 2. Now the matrix Q, in a case of a 2 by 2 system, is just equal to the identity matrix, and essentially whenever the indexes are equal to each other is equal to a 1, and whenever they're not, it's equal to 0 because of the off diagonal element. You just throw that part out of the summation. So whenever the index of the transmit chain equals the index of the spatial stream, then Q is equal to 1. P is a very important matrix, which is shown over here. And for a 2 by 2 system, we actually use a subset of this matrix because ISTS and N would range from 1 to 2. So ISTS is the index from 1 to the number of spatial streams, so that ranges from 1 to 2. N ranges from 1 to 2. So here we have a subset of the P matrix shown here, which is equal to this part, which is 1 minus 1, 1, 1. This sub matrix of the overall P matrix, which is a 4 by 4 matrix in order to accommodate 4 spatial streams, is the same as the matrix we used, the same P matrix that we used in the development of the estimation of the channel using 2 spatial streams. HTLTF, which is indexed over K, which for a 2 by 2 case is a subset of the 4 by 4 P matrix. Again, we have an overall 4 by 4 in order to accommodate 4 spatial streams. So as we index through ISTS and N, we just pick out the value from the P matrix over here. HTLTF, of course, is shown over here. So as K is indexed from minus 28 to plus 28, we pick out a value from HTLTF from here, and that'll either be a plus 1 or a minus 1 or 0 at DC. And of course, we have the exponential designating the carrier, and this is the, of course, amplitude of the carrier. And for each carrier, we know that the carriers are spaced apart at delta sub f, where delta sub f is equal to 312.5 kilohertz in the case of 11n. So K picks out a carrier plus its amplitude. Now, each carrier, recall that it is important to note that when training is performed, between transmit chain number 1 and transmit chain number 2, the symbols in transmit chain number 2 are cyclically shifted by 400 nanoseconds. And that is, we're using CDD when we transmit from the second chain, and also we use CDD when we transmit from in more than 2 chains. For example, in a 3x3 or 4x4 system, then each chain would have a cyclic shift. And the reason for the cyclic shift is that unless we do a cyclic shift, these two symbols are the same, and when they're transmitted from the transmit antennas simultaneously from transmit chain number 1 and transmit chain number 2, they're received at the receiver, and you have possibilities of constructive and destructive combinations which are detrimental to the signal. And by adding the cyclic shift, we actually have a diversity gain, and we have an improvement in performance. Also note that the number of time slots is directly related to the number of spatial streams, and we can actually see this. So for example, if you only have one spatial stream, then you only have one column in this matrix. On the other hand, if you had 4 transmit streams or 4 transmit antennas, you would need to have 4 time slots in order to be able to compute H11, H12, H13, and H14 in the case of a 4x4 system. So here we show that besides the guard interval, we actually add and the cyclic shift is indexed by ISDS, which is the spatial stream index. So for the first spatial stream index is equal to 0 for the second spatial stream. In the second case, for the second spatial stream, it is equal to minus 400 nanoseconds. So this equation is not that complicated once we understand what's going on. Basically, we're generating 2 symbols, one at index n equals 1 and one at index n equals to 2. That's indicated by these 2 terms right here. Secondly, we have the P matrix here, which is very important in order to achieve orthogonality. And its elements are picked out of the P matrix shown over here, the subset of the P matrix shown over here, based on the index for the spatial stream and the symbol number. Q, of course, is a identity matrix shown over here, and we basically make sure that we pick out only the expression when the number of the spatial stream corresponds to the index of the transmit chain. And the exponential represents the carriers, spaced apart 312.5 kilohertz. And as the index K goes from minus 28 to plus 28 in our case, we basically obtain the carriers. Therefore, you can actually generate the time domain high throughput long training fields given the number of spatial streams and number of transmit antennas.